Hey, hello. Uh, so last time we covered front end, basically the database front end, which is the parser, and after that we covered basic query engine and also calcite based query engine. So for the calcite thing, we only covered about the query part, uh, not about the update part and things like that. But yeah, overall you get an idea of what how to implement a calcite query engine. So this time we'll go and look at the storage engine. So storage engine is the uh, uh, part which interacts with the file system in persisting the data. So it's mostly a key value interface. Uh, like if you think about storage engine from a Java in memory data structure perspective, you can think of it like a tree map or something of that sort, or like any map in a sense. So in the case of tree map, we have APIs like get, put, search, and range scan and things like that. So the storage engine will provide those APIs, and those APIs will be reading data from the file system rather than from the memory. So that's the main difference between storage engine and Java maps. And also, storage engine will provide APIs for indexes. So that's also something that will be covered now. All right. So on a high level, the storage engine flow looks like this. So basically, in the query engine, we used to see that like most of the things, like table plan calls heap record scan, which was part of storage engine. So once you call the heap record scan, it will go to this part. So it starts from the heap record scan, which calls heap record page implementation, depending upon whether it's a page based interface. So in the case of B trees, we read data page by page. So we have heap record, or in the case of heaps as well, we read data page by page. So we have heap record page implementation, and most of these pages, uh, in order to be properly managed, we use the page implementation calls transaction. So transaction is a little bit of a complex subject. So normally we have, I think, for the transaction, we have something called as buffer manager, we have concurrency manager, we have recovery manager and things like that. So on a high level, transaction is the component which is responsible for keeping the pages in the memory until a transaction is complete. So by transaction, I mean a series of operation which could be read or write. And when you read a page into the memory, you have to keep it in. You can't read the whole disk file into the memory, right? Because disk file could be like 200 GB, but then your memory is only maximum up to at least my system has around 16 GB of memory. So so we have to properly reuse the memory, or properly use the memory so that we don't overflow. So transaction buffer manager basically takes that responsibility, which is like when you read a page and it's part of a transaction, you keep that in memory. But then when you don't use that, as when you're done with the transaction and a new page needs to be pulled in, and if the memory space is full, you can evict the previous page, which is no longer part of any transaction, and then continue with it. So I think transaction, like the concept of uh, pinning pages and maintaining recovery protocol. So, like I think transaction concurrency and recovery are kind of close related. So, depending upon the con depending upon the pinning logic, or say for example, we'll remove say least recently used or things like that. So, depending upon the pinning logic and buffer manager, we design our own recovery manager, which is uh, so in the recovery space, we have things like a risk recovery protocol. I think that's kind of the standard protocol that we uh, use. So I think it was developed by IBM people in the DB2 project, and it's been there for a while. So basically, the recovery protocol comprises of two aspects. I think one is a steal policy, and the other is force right policy. So stealing is basically when you have a page and you have an array of pages which are in the memory, and you want to uh, bring in one more page, but then like your array is full. So at this time you have to steal a page, and you have to steal the page, but you have to still ensure durability. So when you steal the page, uh, you can allow stealing of page, but then if you don't allow stealing of page, the transaction will be blocked until the page is uh, like page is free. So as in page is no more used in any of the transactions. So you can allow steal or no steal, and depending upon that, the pinning logic also differs. And there is this force and no force. So when you steal a page, like if you allow stealing of a page, you can force writing the page back to the disk, or you can just when you steal a page, you can like temporarily write it to a segment, and once you commit a transaction, you can use that. You can remove that segment, and it's no more needed. But then on a high level, the recovery logics basically depend upon two things. One is steal policy, and the other is force page policy. But yeah, will not be going into that depth in the transaction. I think transaction can be covered when we look into key value store. For now, I haven't implemented the key value store, but if time permits, I might do that, and then that can be covered as a separate video. And as I was telling, transactions talk to file manager by using pages. So any write to the disk. So if you want to modify a key value pair in the disk, you pull in that page which contains the key value pair, and then update the page, and essentially write the page back to the disk. So by doing so, you reduce the write amplification, or like disk usage and things like that. So your disk is not that completely used. You generally page size is either 4K or 16K at the max, or even 1K is fine. 1 KB. So yeah, now we'll go into the code. Alright, so as I was telling, the storage engine typically exposes two APIs. So one is a read only record scan. So record in our case is just the key value pair. So you just have a read only record scan and a read write record scan. So read only record scan, basically it's a iterator kind of interface. We have the next function which goes to the next item. We have seek to query start. So since it's a read only uh, interface, we have the function called seek to head. Instead of seek to head, I just renamed it as seek to query start. And then we have this get int and get string. So depending upon, so when you call the next, you move to the next record. So at that time, your record will consist of multiple columns and multiple fields and corresponding field values. So when you go to a record, if you want to fetch out a field value, then you just need to pass in getInt, call the getInt function with the corresponding field name, and you get the corresponding value. And if you so for getInt and getString, basically we are passing on the data types. But if you want it to be generic, you can just call getValue and then it returns whether it returns a D constant. Like D constant, as I told last time, D is just a ordering parameter. So it just returns a constant. Constant can be either integer or string. And finally, we have hash field as well. So it just checks whether the field is there, the field was defined for the record or not, and then finally close. So similar to the read-only record scan, read-write record scan, basically it just extends from the read-only, and it has got additional functions like set value, set int, set string, seek to the insert beginning, and delete, get record key. So basically when you insert a record, you just need to return back the record key so that that record key can be used while adding while updating the index. So that's the core idea of this get record key. And then seek to is used to jump to a particular uh, uh, page or uh, yeah, jump to a particular page uh, or yeah, jump to a particular page if you have the record key. So basically, these two functions are mainly has a close relationship with the indexes. So get record ID will be used to update the index when you insert or update the data, and seek to will be used when you have fetched the record key from the indexes that you previously wrote, and then you have to fast iterate the data. All right, so that's about the read write and read only record scans. And now we have index scan. So index scan is basically CRUD APIs. So we have insert and delete. So here we insert a constant and the corresponding record key. So this was the one that I was talking about. So basically, once you insert, you get this. When you call the get ID, you get the record key. And now you will be updating the corresponding index value. Say in the previous case, we were creating an index on A. So the A value is 1. We'll put A's value 1 here, and then the corresponding record key, which was where the record was saved in the file. So that will be used. And then similarly, delete has a similar thing. So yeah, seek seek is basically used to go to that particular point, and then has next and next is used to kind of uh, used for iteration. So basically, when you create a while loop which has got has next in the condition, and then until the has next is false, you call the next function and then go on. All right, so that's about the read and data scans and the index scans. We'll see implementation of data scan. So data file organization can be broadly classified into 4 types. Data can be persisted into the disk in the form of B trees, or in the form of heap, or in the form of LSM. So B tree and LSM are like very popular. Basically, when we persist the data, we either persist in as B tree backed or LSM backed. So B tree is known for its uh, low right. Sorry, B tree is known for its basically LSM is known for its low right amplification and uh, wait a second, what was it? Yeah, so here's the thing. LSM is good for uh, write write optimized workload. So if you have a lot of writes, then LSM would be good, and if you have a lot of reads, then B-tree would be good. B-tree basically updates the data in place. Yeah, your data is updated every time you modify, and in the case of LSM, it's just an append only log, and that gets compacted over time. So it will be eventually sorted and eventually optimized for reads, but then it starts off by appending to the log and then persisting in the data level by level and things like that. So on a high level, when you have a write heavy workload, you go with LSM, and then when you have a read heavy workload, you go with B-tree. I think there is also something called as ISAM, uh, ISAM or something. But then, yeah, let's maybe focus on these three. Mm, so for this project, we have heap-based file organization. So a heap record scan implements read-write record scan. So here you can see that we are passing in the table name. So table name dot TBL will return the corresponding table loaded into the disk. So basically, we create the file name and then we check if the file transaction size for that file name is 0. If it's 0, then we create a new block and move to that block. If it's not 0, then we go to the 0th block. So basically, what we are doing is if the file is completely empty, then we create a new block and then go to that block. If it's not completely empty, then we go to the 0th index or 0th block. Okay. So I think heap record scan in this case, you can see that for the catalog tables like TinyDB table and TinyDB column, we have used this constructor and we are passing in the table name as well. All right. So seek to query start, basically as I told in the case of heaps, we start from the beginning of the file and then we iterate over one by one. So we go to the 0th block and we start from there. Okay. And next is basically a function which jumps blocks at a time. So within the block, if you have records 100, if you have 100 records, as in if you have records which are not yet read, then you continue calling the next and you continue iterating the records within the block. But if the block is at the end, if the record pointer is at the end of the block, you check whether there is any further blocks available for reading. If there is further blocks, then you read that block and then continue with the records. If there is no further block, you return a false. Right. So first thing you do is you use the record page to find the slot after the current slot. So current slot is just a global variable which will be used, which will be updated whenever we do a scan. And if the current slot is less than 0, that means that you can find a suitable slot in the block. So you check whether it's a last block or not. If it is, then you return false, else you go to the next block by incrementing the block number by 1. So you increment the current block ID's block number and then go to the next block, and then from there on, what you do is uh, you find the next beginning current slot for this new block. Okay. Get in this, so all these functions will be calling the record page implementation. So we see that record page dot get in is used. So this read write record scan is like the key value interface for the upper level uh, components like query engine and things like that. So it basically doesn't have the concept of slots and things. So it just abstracts out the slots, block ID, and all those information in this class, and delegates it to record page. So you can say this class is kind of a facade interface for the underlying page-based or whatever based implementations, right? And get value, so basically we check whether the schemas, from the schema we check whether the data type of this uh, uh, thing is integer or not. If it is integer, then we call the corresponding getIn function, else we call the getString function. So these are the ones. And also we check hash field. So hash field is basically checked by checking the record value layout and checking whether it has got these things. So previously we covered all the read-only record scan implementations. Now these are the read-write record scans implementations. Similar things, just that we have set instead of get. So I think, yeah, so I think most of the things are straightforward. So seek to, okay, maybe I'll go this. So if you want to seek to a particular record key, you need to find what is the block. So in the record key, you have this block number. So um, mm, basically using the file name and the block number, you can get the block ID. So once you get the block ID, you create a heap record page implementation, which replaces the global record page. So from now on, you will be using this new record page implementation, and that will be starting from the corresponding block that we passed. And also the current slot is also, the current global slot is also updated. So we have record keys slot number being updated as the current slot number. So essentially by doing this, you have updated both the record page and the current slot global variables, and when you call the next function, you will be seeing those in those changes. And move to block. So yeah, move to blocks. Block is also kind of similar. So when you go to a new block, you are updating the current slot as -1. So like the next slot which will be read will be after the -1, which is a new slot within the block. Okay. Move to a new block is calling append on the file. So when you call the append, we are actually, okay, when you call append, what you're doing is you're calling the file manager's append function. So what you do is you create a block and you assign a byte array with the block size. Now what you do is you seek to that block size and write the corresponding byte array and then close it. So essentially when you call the append on the file name using the file manager, what you're doing is you're creating a new block. So this is how you create a new block. You create a new block ID. You declare a byte array of the size, block size, and you go to the starting position of the block size. You write the empty block, empty byte array, and you close it. So that's pretty much it. And at last block. So yeah, at last block will check whether what like you have the record page block number, APA, and also transaction dot size. Uh, I think transaction dot size. Yeah, so transaction dot size returns the block number for the mm, So I just renamed it as block count. Okay, so it just returns the block count and whether both of them match. Then it means that it's the last block. Alright, so now at this point we'll go to the heap record page implementation. So yeah, heap record page implementation, as the name suggests, it's a record page implementation or page implementation as such. So uh, here you can see that most of the calls were directly hitting the record page implementation. So let's take one example. So here we pass on what is the slot and what is the field name, and based on that, like so yeah. One thing to notice, let's say we have this move to block, right? So when you move to a new block, you are actually what you're actually doing is you are creating a record page, right? So now for that block you are reading that entire block and you are calling uh okay, so basically block is the name of bunch of records which is persisted in the disk. Okay, when it comes to memory, when the same block is taken to memory, we call it as page. Okay, so most of interfacing will be done on pages. Okay, so now when you move to a new block, you read the corresponding block from the disk and create a page for that corresponding block. Okay, so page is just a counterpart of the block that's on the disk, and at this time, within the block, you want to specify the slot to go to that particular slot and update the value. Okay, so what you do is we use the slot and we call the offset plus the record value offset of the field name. Uh, okay, yeah, this is clear. So offset function would determine what is the record's overall slot size. So if the record consists of if the record consists of two columns A and B, and each of them has the size 4 bytes and 10 bytes respectively, the records size is like 14 bytes, and in that case when you specify the slot you multiply slot with the offset or the record size, and this time 14 into the corresponding slot size. Now you get to the beginning of the corresponding slot. Okay, and from there you have to read what is the offset within the record. So if you want to read B, then you specify that offset and then you can read the value B within that record. Okay, so here you are passing offset plus the record layout offset and things like that. So every function basically calculates the field position and then calls the transaction dot set string. Okay, now yeah, delete basically as we once discussed, delete just marks the header of the record as empty. So in the header we have used or unused byte representing whether the record is used or unused. So when you write a record, it becomes used, and when you want to delete it, you just mark it as empty. So when you do a compaction, which we haven't implemented, but when you generally do a compaction, you can remove all those empty things. So I think format, okay, format is used when, okay, let me see, transaction, Okay, so format is used when you want to remove a particular. Uh, oh, okay, got it. So yeah, here's the thing. So format is just the way you use format in the disk. So if you want to format a particular disk, or when you in Windows, if you do a format, you remove the you clear all the contents, right? So basically when you delete an object, it's not getting deleted in the disk, it's just getting soft deleted. So on a high level, what you're doing is basically you check whether the in the new block whether the slot is valid or not. You start with the big first slot or zeroth index, and then you mark the first item as empty, and then you go to all the fields. You check whether the field value, previous field value was integer. If it was integer, you mark it as 0, and if it was string, you remove the string value. So on a high level, what it does is it's just doing formatting similar to the one that we do in the disk. Find slot after. So uh, yeah, that is basically checking for the slot which is after a particular slot and after used, so it should not be used, I guess. I'll go this once we go to the search function. I think it's just three functions down. We'll go over that, okay. And insert after. So insert after is also basically first calculating what is the new slot, and then we check whether the new slot is greater than 0, which means that we have something. And mm, okay. I think at this point we'll go directly to the search after. So, okay, we what we are doing is we are checking whether the slot is valid. If the slot is valid and if the transactions flag is similar to this thing, then we return the flag. Okay, all right. So what we are doing is we iterate over the slots. Okay, so slot 0, slot 1, slot 2, all these are basically records within the block. So we start with the first slot, we check whether it's a valid slot or not. By checking whether it's a valid slot, what we do is we check whether the slot has crossed the block size or not. Okay, if it has not crossed and if it's a valid thing, what we do is we capture the offset of slot, and like we check whether the records flag is equal to the flag that we set, uh, we passed as an argument. So if we want to find a slot which is used, we keep it as used. So until so if the value is used, then you return the corresponding slot. If it's not, then you increment the slot number and then go on until you find the. And if it's not found, you return -1. Okay, so let's go back and see the use cases. So find slot after mm, this thing. So all right, so in this case, you can see that next is calling the find slot after. All right, so what we are doing is we want to find all the slots which are marked as used, which is basically written slots, and you want to iterate over those slots and fetch the values. Okay, so find slot after is fine. You're reading all the use bytes. Now insert after is another thing. So basically, what we are doing is we are finding the first slot which is kind of empty, and where it's a valid slot. So uh, uh, I think let's see the usage. So yeah, so we return. All right, so here you can see that what we are doing is we try to capture the first empty slot, and if we got a valid slot, then we mark it as used, and then we send it to the corresponding callee, and also we return the corresponding slot number. So in this scenario, we are checking the first thing, which is we are checking whether the corresponding slot that we received is valid. So if we couldn't find a slot, we'll return a value negative. So if you get the value negative and if we find that it's the last block, then you move to a new block. If it's not the last block, then sorry, if it's the last block, you create a new block. Right, and if it's not the last block, you move to the new block and then call the current slot function again. Okay, so I think search after is also fine, and then if it's a valid slot, basically what we are doing is whether we're checking whether the block size is crossed or not, and then for the offset, what we do is we capture the record values layout slot size, and then yeah, basically this slot size is the total size of all the items within the table record. So I think this is like the final position of the record. So if in this layout we have in use, which is of 1 byte, and that's the header of the record. Then we have A, which is of 1 byte, and again, and then B of 5 bytes. So slot size will be comprised of 1 plus 1 plus 5, which is 7. So that part is clear. All right, so we have covered heap record page, and then record key is basically a combination of block number and slot number. So this will be used in the index. Whenever we put an item into the data file, we return back the record key, and then we use the record key in the index to do the persistence. Okay, so that's about the uh, data file. So I'll quickly go over the files and then file and transaction, and then we'll go back to the indexes. So in the file we have block ID. Block ID is nothing but a file number, file name plus the corresponding block number, and page is just the, as I told you, page is just an in-memory counterpart of block. So block is the one that's saved in the storage, and page is the one that's persisted in the memory. Not persisted, that's kept in the memory. Uh, so it's basically a byte buffer, and then you use the APIs called get in, set in, and all those things to kind of read and write from the byte buffer. So I think that should be okay. Like byte buffer is like it's just an abstraction of byte buffer. So byte buffer is uh, the one that's read from the block. Okay, so that's pretty much about the page, and now we'll go over the file manager. So file manager is the core API which is responsible for all the IOs onto the disk. So it mainly as I told you, it mainly deals with the page and the block. So let's see the read function. So first, what it does is it just fetches the corresponding random access file. So random access file is just opening a file in the form of random access file, read write access. You seek to the particular block number using block number and the block size. So now you go to the starting point of the block. Now what you do is we call the get channel function to read the contents of that particular block and pass it to the p contents. So I think p contents is basically setting the position of the block byte array. Uh, byte buffer to 0, and it's just returning that byte buffer. So what would be the content that you got from the file it will be run down to the contents, and finally we close the file manager. So essentially what we are doing is mm, we are using this content function to update the uh, byte buffer. Okay, and whenever we call the page, we are actually setting the block size here. So like byte buffer, the contents is kind of by default allocated the byte buffer, and whatever you read to the byte buffer, you have the block size being read from the disk. And similar goes with the write, and I think we have covered append previously, so that's also fine. Block count is basically finding the length and then block size and dividing them so that we get the block count. And then I think that's pretty much about the file manager. Okay, and now we'll cover the transaction, right? So I think this is fine. We are not using it. So recovery manager is also fine. Buffer manager is also fine. We are not using it. Transaction. So on a high level, what transaction does this? It has got file manager and buffer manager. We are not implementing buffer manager. Uh, so ideally, all the transaction will be given some sort of a monotonically increasing number called transaction number. And in the commit, rollback, and recover, we have not implemented it, but then ideally in the commit we should have the logic of pinning the sorry yeah, we have the logic of pinning the concurrent pages, pinning the transaction pages, and also writing to the write ahead log and all those things. And rollback and recover is also kind of linked with the commit logic and things like that. So I think most of these things in the transactions are unimplemented. So maybe once we go over the key value stuff, we can revisit this. But yeah, so now we have getInt. So getInt is basically function to read the page and then call the contents.getInt function. So getInt basically it just calls the page getInt function, and similarly getString also does the same. So I think on a high level, as I was telling in this diagram, transaction calls file manager via pages. So if you see all those getInt and all those functions are basically file. We create a page and then we call the file manager, and then we return the page content using the page APIs. Okay, so that's about the transaction. Now we'll go on to the index. Okay, so we can implement index using hash index or B plus tree, or extendable hashing and things like that. So in this case, we have used B plus trees, and I think B plus trees. We have implemented two sorts of BPlus tree. One is the basic BPlus tree. I think this is taken from the SimpleDB project. So I'll not be going into the depth of BPlus tree here, but then uh, we have also used the library. I think the library was from David Morton. So using that library, we have implemented a BPlus tree. So on a high level, uh, we are calling the APIs for the BPlus tree, which is, oh, sorry, I think this is the test case. Yeah, uh, but I think this is a really great library that he has built. So we can pass in what is the directory, and then we can pass in the maximum leaf size, non-leaf size, and all those parameters are passed via builder pattern arguments. And we can finally pass in the serializer, deserializer, sorry, serializer interfaces. So in the case of constant, so in our case, the B tree index is going to have key as the constant and value as record key. So key is basically, as I told you, when we create an index on A, key is going to be A's value. So it can be either a string or an integer. So in our case, that's why we use a constant. And value would be record key, which is the point where it got inserted. So finally, when we insert record, we are passing in the records via like constant one and two, and then finally record keys this thing. Okay. All right. So I think this part is just a test case. So basically, we try inserting two records, and then we call the one find function to loop through the records. Okay. So I think this same thing will be used in this index implementation. So as we discussed, we have insert, delete, seek, has next, next. So yeah, we have we are going over the uh, we are creating the tree in the constructor, and then we are calling all the insert, delete. Delete was not there in the I think not implemented by the library. So uh, it's not supported by the library that we are using, so we haven't used it. So and seek is basically the find function with iterator. Has next checks whether there is any record after this, so we call the has next function, and then next is used to go over the next record. And I think this can be removed. We are not using it. So constant serializer. I think this is one thing that was missing in the documentation of that library. So well, figured it out. So in the case of constant, we are I think for simplicity's sake, we are creating it as integer. So if a equal to if we are creating an index on a is of type integer, so we are creating the index assuming that it's integer, and we are also putting integer into this thing. I think this will make more sense we go into the record key. Alright, so in the case of record key, we have two items. One is block number and the other is slot number. So for the block number and slot number, we are using get in function from the large byte buffer pool. So large byte buffer pool is a object or a class that's provided by the library. So we have to use those APIs to get the corresponding value, and finally we get once we get the values, we create a record key and then return that object. So read will return your record key. And when you write the record key, you have to use the put in function to kind of get the block number and the slot number, and the call put in iteratively for passing on the arguments. And finally, maximum size is basically the size of 2 bytes, two integers. So that's why we are adding integer bytes plus integer bytes. In this case, we are returning integer bytes alone, so that's fine. All right. So on a high level, as you can see, this is using the library, and I don't completely understand this class, but then maybe I think I'll take some time to dig into the index, B-tree index, actual B-tree index, and also cover the some concepts of transactions and things like that later in this series. All right, I think that's pretty much about it. For the libraries, we have used Lombok, David Morton's BPlus tree library, and Calcite as well, and then Sharding Spear. Cool. Mm, yeah, as you can read from the documents, we have the front end query engine, text and storage engine, and CLI interface. Well, I think that's pretty much it for now. Let's wrap it up. All right. See you guys in the next series.